Hi everybody, this lesson today is lesson 8.1. This is the first lesson in Unit 8. Unit 8 is going to cover exponential functions and logarithms. Today we are just talking about exponential growth in general. So some things to talk about is what is linear growth, what is linear decay, and how does that compare to exponential growth or exponential decay. So linear growth is when something goes up by the same amount each time. So if your parents are adding $20 to an account every week, then it's adding $20 every week. Your slope would be going up $20 every week. Linear decay is if it's going down by the same amount over time. So if there's a bucket leaking water and it starts off with 20 gallons of water and it's losing so many per hour, then it is going to be linear decay. We don't usually call it linear decay, but that's really what is going on. Then exponential growth. Exponential growth doesn't go up by the same amount every time. It goes up by the same factor or the same percent over time. So, for instance, cellular division. It's not going up just by the same, you're adding a cell every time or adding 5 cells every time. You're adding 1 cell and then those cells are dividing and they add 2 more and those cells are dividing and they add 4 more and those cells are dividing 8 more, et cetera, et cetera. And so you have more of a curve like this, exponential curve. Exponential decay is the same thing, it's just going down. So again, we have something that's going down over time by a certain percent or a certain factor. So for instance, maybe you have a species population that is declining and maybe it's going down 10% every year. So it's going down 10%, down 10%, down 10%, down 10%, etc. And it's getting smaller every year. How does that different from exponential or how is linear different from exponential or decay? Well, the main thing is that linear is the same amount every time. Exponential is the same percentage or factor every time. So you're adding $5, but on this one you're adding 5%. The standard form of the equation for exponential growth and decay is this y equals ab to the x, where a is not equal 0, otherwise it would just be 0. B does not equal 1, because in that case an exponent wouldn't do anything, and x is a real number, so it's not imaginary. In this case, A is your starting point, your y-intercept or your starting point. B is your growth factor or decay factor. So again, like with cellular growth would be 2 to the x because every time it's doubling. But it doesn't have to be twice as much every time. There's lots of different factors that you can go up or down by. So B is the growth or decay factor. If B is greater than 1, it is exponential growth. If B is less than 1 or between 0 and 1, it is exponential decay. And this is kind of a big deal. This is kind of like when COVID was around and everyone's saying we want to, make sure we don't give it to anybody, because if one person is giving it to 5 people, you're going to have this huge growth curve and it's just going to go way up and skyrocket. Whereas if you can say if one person's just giving it to one person, then it's going to stay constant. But if one person actually is only giving it like for every 2 people, only one of them gives it to someone, it's going to go down. And so if the B here, the number that is being taken to the power, if that growth factor is greater than 1, you're going to have growth. If that factor is less than 1, you're going to have decay. If it is 1 itself, it's just going to stay constant. All right, what do these graphs look like? Well, the graphs will make a shape just like kind of those sketches I've been drawing a second ago. So let's consider the function y equals 2 to the x. Let's plug the numbers into x and see what we get. I think it's always easiest to start with 0. 2 to the 0 is 1. Anything to the 0 is 1. 2 to the first is 2. 2 to the second is 4. Now, negative 1, 2 to the negative 1 power is 1/2. And 2 to the negative 2 is 1/4. Okay, let's go ahead and graph those points. On your graph over here, try to make we're going to count to 4. That's as high as we're going either way. And so try to make your segments, sections kind of big. So I'm going to go like this, go to 4, go to 4. Over here, I might not go to 4. And over here, I might just go to 3 maybe. All right, so we're going to set up our graph. We're going to graph it. So 0, 1, 1, 2, 2, 4, and negative 1, 1/2, negative 2, 1/4. And that's why I wanted to make those tick marks kind of big increments between them, so we had room to put a 1/2 and a 1/4. Of course, next one would be 1/8 and 1/16 and so forth and so on. So in other words, as you might be thinking, we do have an asymptote, okay? Our asymptote is at y equals 0. The domain is from positive infinity to positive, negative infinity to positive infinity. And the range, it will never hit 0. So it will be from 0 to infinity, but it will never hit 0. All right, there's no number you could plug in for x that would land us at the 0. So that's going to be our asymptote. All right, let's take a look at what if it goes the other way. This one's going to be decay. Remember I said if it was greater, if the growth factor was greater than 1, it will be growth. If the growth factor is between 0 and 1, it'll be decay. So this one will be decay. So let's go ahead and plug some numbers in and see what we get. Once again, I like to start with 0. 1/2 to the 0 is 1. 1/2 to the first is 1/2. 1/2 to the second is 1/4. And then negative first power is 2. Negative second power is 4. And again, I'm going to try to make some larger spaces in my graph so I can fit in those fractions if I need to. All right, so I've got this set up. Negative 2, 4. Negative 1, 2. 0, 1. 1, 1/2. And 2, 1/4. It's hard to get down that small, but there we are. And we're going to draw in our curve. It's going to get closer and closer and closer to the y-axis, or excuse me, the x-axis, but never touch the axis. So our asymptote, once again, we have an asymptote at y equals 0. It gets closer and closer and closer, but never hits it. The domain is, again, from negative infinity to positive infinity. Now the range, is the range the same? Well, actually it is. It also goes from 0 to infinity, but it does not include 0. One thing before we leave this video is I want to talk about the y-intercept, and this should happen with any parent function. So both of these cases are parent functions, and both of them have a y-intercept at 1. And so that actually is quite important for us to know, so that we have a y-intercept at 0, 1. This y-intercept here is at 0, 1. Unless there's some sort of like adding 5 onto the end, which would move everything up, of course. So it would move it all up 5 units. But otherwise, we're going to have a y-intercept at 0, 1 on every parent function that we have. And I say every parent function because these are all like separate different parent functions. One last thing I want to mention is some of you might be thinking, well, isn't a parabola exponential? The difference here is in the exponential, the x, the variable, is actually, the exponent is, the variable is the exponent. So in this case, in the parabola, that was not exponential because the exponent was a 2. And an exponential, the exponent varies. It's an x. So it could be to the 5th, to the 2nd, to the 9th, to the 20th, whatever. So that's where we're plugging in those numbers to. Okay, I wanted to clarify that. That is just a basic introduction to exponential growth and decay. We will spend a lot more time in this unit exploring some of these concepts.